We are checking out Newton's law of cooling, which is an exponential model that says that the temperature of an object a heated object will decrease exponentially over time towards a certain temperature. So it'll look something like this. It's not, let's try that again. So the object is going to start at a certain temperature and decrease over time towards a certain temperature. Okay. So the equation for Newton's law can be modeled by U of t equals t plus u sub naught minus t times e to the t k times t time. And k is a it's a number that is smaller than 0. Okay, so it's negative. So a couple things. U is equal to the object, the heated object, the temperature of the heated object at a certain time. Capital T is the constant temperature of the surrounding object. So it's like the room temperature, basically. U sub naught is the initial temperature of the heated object, and K is the negative constant. So we have a situation, an object is heated to 100 degrees Celsius and is then allowed to cool in a room whose air temperature is 30 degrees. So I see some things right now. 100 degrees is U sub naught because that is the initial temperature. And 30 degrees is the temperature of the surrounding object. So it's the air temperature. So it's the temperature surrounding the object, which is equal to 30 degrees Celsius. So it says if the temperature of the object is 80 degrees Celsius after 5 minutes, then what is the temperature? When will the temperature be 50 degrees? Okay, so what I know right now is that we need to write an equation. So U of 5 would be the time, and it is a temperature of 80 degrees. Okay, U sub naught is equal to 100 degrees Celsius, and the temperature of the surrounding temperature would be 30 degrees Celsius. So when I'm writing my equation, I can use this information to fill out U of t is equal to, and the capital T is 30 degrees. So I'm just going to write 30. You know what? I'm going to write the equation. It's T minus U naught minus big T times e to the k times t. So we can start filling in the information we know. I have 30 plus 100 minus 30. That's basically the possible change in temperature, to the e to the kt. All right, so simplified, I get U of t is equal to 30 plus 70 e to the kt. And I have too many variables here, so it's time to plug in our initial condition of U of 5. So I know that U of 5 is equal to 80, which is equal to 30 plus 70 e to the k times 5. All right, I'm going to subtract 30, giving me 50 is equal to 70 e to the 5k. I need to get the base of e by itself, so I'm going to divide both sides by 70, leaving me with 5 over 7 is equal to e to the 5k. The unknown is in the exponent, so it's time to change forms to logarithmic form. And I get ln of 5 over 7 is equal to 5k. Divide by 5, and I get the exact value. So k is equal to the ln of 5 over 7 over 5. That's the exact value. The decimal equivalent is negative 0.0673. Negative 0.0673. Okay, I'm going to pull out my calculator now. All right, so I calculated the ln of 5/7, close the parentheses so that the 5/7 stays your input, divided by 5. I want this number for later. So I'm going to store this number. So stow is above on, alpha A. And that way I can use, instead of plugging in the decimal, I can just use alpha A in my calculation. Okay. So the next step, I would like to set up my equation now that I know what my K value is. So I need to write U of T is equal to big T, which is 30, plus 70 e to the K, which is negative 0.0673 times T. So, which I stowed as A, which is A for me. Okay. All right. So what the question asks is, when will the temperature be 50 degrees, basically? When will the temperature be 50 degrees? So I am going to plug in, what we're trying to find is U of T, when will U of T equal 50 degrees? So I'm going to set my equation equal to 50. So 70 e to the negative 0.673 t. Okay, in my calculator, I am going to use A for my calculation. Okay, so, but I'm not there yet. So minus 30 from both sides, I get 20 is equal to 70 times e to the negative 0.063 t, divide by 70. My zeros cancel, leaving me with 2/7 is equal to e to the negative 0.063 t. I will change the form. Okay, so ln of 2/7 is equal to negative 0.063 t. Divide both sides by my A value, which is 0.063673. I forgot a 7. Okay. 73. Okay. Okay, so when I plug this into my calculator, I get T is about equal to, okay, I'm gonna go ahead and plug this in my calculator now. Whoa. Okay, I have ln of 2/7 divided by alpha A. And I get 18.62, and time is modeled in minutes. Okay, so that's how we would figure that out. So the next thing it's asking us is to graph the function. So just looking at what the graph looks like. So I'm going to go ahead and press my y equals. And for y1, I just want to write the function u of t, which was 30 plus 70 e to the negative 0.0673 t. But remember, we want the exact value for our multiplier. So I'm going to have e to the at is what I'm going to write for y1. So I'm going to do 30 plus 70 e to the, oops, I had alpha instead, e to the alpha a times x. So in my calculator, I'm actually going to write y1, and then I'm going to use an x instead of a t. Okay, and I'm going to go ahead and graph this. And I know that if I plug in a 0 for the time, 30 plus 70 times e to the a times 0, I get e to the 0, which is 1. So this is 30 plus 70, which is equal to 100. I can see that my initial temperature is 100 degrees. So I'm going to want to make sure that my window shows 100, at least a height of 100. Okay. And then it looks like maybe I want to see more time. So 25 minutes, maybe. Actually, let's go to 30 minutes. So X it represents time. So you can see the curve start to flatten out. Okay. All right. So that is B. Really, we're just looking at the graph. Okay. Part C, it's going to ask, determine the elapsed time for the object at when the object is 35 degrees. Okay, here's how we do this one. We're going to set y equal for part C. We're going to set my y1 equal to u of t, which we've already done, and my y2 equal to 35, because I want to look for the intersection when y is 35 degrees. See, I'm going to graph. Ooh, my intersection is off of my screen, so I actually need to extend out my window. I'm going to just extend it to 50. Okay, so on the right side, I need to extend it. Now I'm going to use my intersect feature, which is second trace. Then I press 5 or scroll down to intersect. Okay, on the blue curve, I'm going to get close to the intersection. Press enter when I think I'm close. Now I switch to the red curve, get close to the intersection, press enter one more time. And it says my intersection is basically u of t equals 35 when t is about equal to 18, oh, not 18, 39.22. 22 minutes. All right. And then the last question asked me, so what do you notice about the temperature as time passes? In other words, describe you as the temperature increases. So we're talking about end behaviors. Part D. As t increases to infinity, well, let's look at our window, and we're going to change the y max to something like 300, just so that we can see a really wide, long amount of time. Okay, so I'm going to graph, and I can see as x increases, my curve is approaching, and if I press trace, I can look at the outputs. It is approaching the value 30. Am I ever going to really make it to 30? Not really. There's always going to be a small decimal there. Okay, but we will approach. So you will approach 30 degrees Celsius. It won't make it, but it will approach there. All right, that's it for today.